In this video, we're going to take a look at the law of sines, which is kind of a big topic in trig. We end up learning about law of sines and law of cosines so late in the year that we don't get a chance to use them much, but they're actually really useful for us because they allow us to work with non-right triangles. My plan for this video is to start with some more abstract conceptual stuff about like where the law of sines comes from, and then we're going to use it. We'll have 5 examples where we'll see how to solve triangles using the law of sines. So we're going to go way back to geometry. You got to remember that when you're labeling a triangle that we use uppercase letters for the angles and lowercase letters for the side lengths. And remember that the side lengths always go across from the angles. So if angle A is in the bottom left, side A would be the top right, side B would be the bottom, and side C would be the top left. And we're going to be using the law of sines to solve triangles, which just means to find all of their side lengths and angles. So it will be important that you use uppercase and lowercase letters to keep these things straight. Another thing you learned in geometry are these triangle similarity cases. And honestly, the only reason we talk about these is we can use them to organize what type of work we're going to be doing. So if you're ever given an angle side angle, or side angle case, you know that you're going to have to use law of sines. We'll get to the law of cosines later, but just so you know, the 2 cases that fall under law of cosines are side and side angle side. Now, in case you forgot, these letters, like the AAS, means angle side, and it means that those are the 3 pieces of the triangle that we know in that order. So we know one angle, we know the angle next to it, and then we know the side touching that second angle. So in the angle side case, imagine first I gave you a side length. Like imagine I gave you a popsicle stick and said make a triangle with one of the sides being exactly this long. So that side length is staying constant, and now the angle touching it is also staying constant. I know exactly how big that angle should be. And I know how big the next angle should be, I just don't know where exactly it should go. And since I don't know the lengths of these sides, I'm just going to have to leave them as dashed lines, and then this angle can kind of just slide back and forth. But you see that when I do this, there's only one spot where this angle forms a complete triangle. So the angle side case only ever has one possible triangle. For the angle side angle case, imagine you know what the 2 bottom angles would be on a triangle, and you know that the side connecting them is some certain length. So none of those 3 things can change. The only things left are these 2 top sides and the top angle. But there's only one possibility that actually creates a triangle. So these 2 are like the best case scenario. Unfortunately, we also have the SSA, the side angle case, which we also refer to as the ambiguous case. And you probably remember in geometry joking about if you spelt this backwards, right? So this is the bad case, and the reason why is there's sometimes 2 possible triangles. So let's like build up some hypothetical triangle. I like to compare this to like the Goldilocks story. So imagine you have this angle, this side, and then this top side. But if this top side is too small, you can like swing it back and forth and it will never touch the ground. So there's no possible triangle here. If I gave you a different problem, we could have, okay, so like the same angle, same side, but then if we take this last side, if we made it too long, we could actually make 2 separate triangles. There's the one with the side like swung out and with the side swung inwards. And then if that side length is just the right length, it will drop straight down and just make one triangle. So let's take all this information, just kind of put it on hold for a minute, and we're actually going to derive the law of sines. And we'll use the same triangle we had drawn before, so I'm going to label this the same way. Now, to derive the law of sines, the idea is like we want to use stuff that we know to prove something that we don't know yet. And the big problem right now is this is not a right triangle, so I can't use any of the trig that I've learned so far. So to fix that, we have to make some right triangles. So I'm going to drop a perpendicular line from angle B down to side B. So now I have these 2 right triangles, the one on the left, the one on the right. And let's call this dashed line in the middle H, like H for height. And now we can actually start setting up some sine equations. For instance, we could take the sine of angle A, and that would be sine is opposite over hypotenuse. So don't get confused about the H, because H is not for hypotenuse, but we could say sine of A is H over C. And I could do the same thing for angle C. I could say that the sine of angle C is H over A. Now I'm not going to do the same thing for angle B, because if you look at sine of angle B, well, the problem is angle B is this whole thing, and that's not part of a right triangle. That's like including both of the right triangles that we just drew. So we're just going to ignore B for a little bit. But both of these equations have an H in it, so let's solve both of them for H. This one, I'll just multiply that C over to the left, so we'll have C times the sine of A equals H. And then for this one, just multiply A over to the other side. So we'd have A times the sine of angle C equals H. So if both of these things equal H, we can just set them equal to each other. we could say C times the sine of A equals A times the sine of C. Now there's one more step we can take that's kind of nice. If we just divide both sides by A, for instance, that would cancel both of those out. And then if I also divided both sides by C, that would cancel both of those out. And now we'd be left with this, sine of angle A over side A equals sine of angle C over side C. So it's a nice and organized equation because the A's are together and the C's are together. And you could do the same thing for B. So I'm going to extend this and say sine of angle B over side B. All we'd have to do to make this work is just basically redraw this whole setup. And then instead of drawing a line from side B to angle B, we would just draw a line from side A to angle A and run through the whole thing again. And then we'd be able to take the sine of angle B. Now it's kind of weird that this is a 3-part equation, but we only ever work with 2 pieces of it at a time. So maybe these 2 pieces, maybe these 2 pieces, maybe just these 2. Because for instance, if you just isolate just these 2, you'll always be given 3 pieces of a triangle. So let's say you're given angle A, side A, and angle C. Then you could use this equation to solve for side C. Or let's say you're given angle A, side A, and side C. Then you could solve this thing for angle C, etc. And actually, while I'm talking about that, there's another form of this entire law of sines equation. If you just flip the entire thing around, you could say A, side A, over sine of angle A equals side B over sine of angle B equals side C over sine of angle C. I like to use these equations anytime I'm solving for an angle because the angle is already on top of the fraction, so it basically eliminates one extra step. And I like to use these if I'm solving for a side length because again, the side length is on top of the fraction. So we made it through all the conceptual stuff. Now we're just going to work through 5 examples. So grab a calculator out and follow along with the calculations as we go. I already have all of these values worked out ahead of time sitting next to me, just so that I can focus more on solving the equations with you instead of just talking about calculations. But you'll want to practice typing this in and make sure you get the same values as me. Alright, so jumping into number 1, it says use the given information to solve the triangle, and the information we're given is angle A, angle B, and side A. So this is an angle side case. Again, this is not the most important thing, it just tells me that there's only going to be one possible triangle. So the fact that I have 2 angles tells me it's going to be really easy to figure out the third angle, because I remember that all of the angles in a triangle have to add up to 180. So if I have 10 degrees and 60 degrees, add those up and subtract them from 180, you should get 110 degrees for C. So now we know all 3 angles, I just have to figure out the other 2 side lengths. And to do that, we'll set up the law of sines. So I'm given side A, and I have to put that in a fraction along with angle A, and I also have angle B, and I could use this to solve for side B. So since I'm solving for side B, I'm going to put that on top, B over, and then sine of angle B, and then just use a pair of information that you know, so side A and angle A. So I'll say 7.5 over the sine of 10 degrees. Now we just have this little equation that we have to solve for B. In order to get B alone, I just need to get rid of this denominator, so I'm going to multiply both sides by a sine of 60. Just kind of ran out of room on the left there, but that would cancel this out, and we'd end up getting B equals, and now this is what you would type into your calculator, so 7.5 times the sine of 60 over sine of 10 degrees, and when you do that, you should get 37.4. So we already had all 3 angles, and now we have 2 side lengths. I just need to figure out the third. So I know side A, side B, I've got to figure out side C. So I'm going to use the law of sines just like I did up here. Okay, so I'll say side C over sine of angle C, and we had to figure out that angle C was 110 degrees, and then just use a pair of information that you know. Now, since I know side B, I could set up a fraction with side B over sine of angle B, but I like to always go back to information that was given to me in the problem, because if I get this answer wrong, then that's just going to make the next answer wrong as well. So I'm actually going to set up 7.5 over sine of 10 degrees again. And again, we would just have to multiply the sine of 110 degrees on both sides, and that should get you C equals 40.6. And that's it, we solved the triangle. We now know all 3 angles and all 3 sides. If we take a look at number 2, we have an angle, a side, and a side angle case. And that's that ambiguous case. So I have to be a little bit worried that there might be 2 possible triangles. But if you look a little closer, angle A is 105 degrees and 15 minutes, which just means, so we have 105, and let's see, there's 60 minutes total, so 15 would be like a quarter of that, so 0.25. So we have 105.25 degrees. One of the angles is already obtuse. And since they give us an obtuse angle, there's only one possible triangle. Okay, so let's jump into this problem. So we're given this angle A and side A. That's a pair of information that we know. I have side B, and let's find angle B. Since we have side B by itself, let's start by finding angle B. So I'm going to use the equation with sine of angle B on top because that's what I'm solving for, and I want it to not be in the denominator. So that would be over 15, and then it would be sine of angle A over A. Now to solve this equation, again, we just want to multiply 15 on both sides to get that out of the denominator, and then just type this into your calculator. So sine of 105.25 times 15 over 120. And doing that should get you 6.9 degrees for B. And now that we have two of the angles, I'm just going to find the third one right away. And since all three angles add up to 180, I'll say 180, subtract the 6.9 that we just got, and then subtract the 105.25 from the beginning of the problem. That should get you 67.85 degrees. And the last thing we have to do is just find the third side. So I want to put that side length on top, side C, and then we'll put sine of its angle on bottom. We just figured out angle C was 67.85 degrees, equals, and then again, pick a pair of information that you know, and I like to go back to the beginning of the problem and use the information they gave you just because you know that's correct. So I keep running out of room when I'm writing these, but here you'd want to multiply both sides by sine of 67.5 degrees. That'll get that out of the denominator, and that would get you C equals 115.2. So once again, we've solved our triangle. All three of our next examples are that ambiguous case side-side angle, which means that we could have 0, 1, or 2 triangles show up. So let's see what happens. In number 3, we're given angle A and side A, so that's the pair that I'll want to put together. And since we have side B by itself, let's figure out angle B. So I'll put sine of angle B on top over side B, which is 12.8, equals, and then sine of angle A, which is 58 degrees, over side A, which is 4.5. So we'll multiply this 12.8 out of the denominator, and that would give us sine of B equals some number, which I'm not going to type this into my calculator yet, just because I don't want to bother with decimals. And just a helpful tip would be sometimes it's nice to take this 12.8 and put it in front, just because when you have it after the sine function, then you have to make sure to put parentheses around the angle, so just putting it as a coefficient is a little bit easier. But our next step in solving for B is to get rid of this sine, which means we need to take the inverse sine of both sides. Now this is going to be kind of a lot to type into your calculator, but it'll just be one step and then you won't have to worry about rounding errors. But what you'll find is when you type this in, your calculator is going to say something like undefined or some kind of error message. And the reason for that is remember that the inverse sine has a finite domain, like you can't just plug anything into it, and this number ends up being outside of that domain. Like 12.8 over 4.5 is around 3-ish, and since that's so much bigger than 1, it's going to be outside of the domain of inverse sine. So our first result is that we got an undefined angle, and that just means that there's no possible triangles. So this information they gave us does not make a possible triangle. And since we're solving triangles, if you want to answer this as no solution or no triangles, that would be perfectly fine. So moving on to number 4, this time we have angle B and side B, so that's the pair that I'll put together, and I'm going to look for angle A since I can match that up with side A. So we'll say sine of angle A over 4.5 equals, and then sine of angle B. Now B is 15 degrees and 30 minutes, so that would be 15.5, right? Because 30 minutes is half of a degree, over, and then side B, which is 6.8. Once again, I want to get rid of that denominator, so I'll multiply both sides by 4.5. But I'm not going to use my calculator yet. I'm just going to write all this out, and then take the inverse sine of both sides. And doing that should get you 10.2 degrees. Now here's where I'm going to introduce a new step. Because in the last two examples, we did have the ambiguous case, but there was only 1 or 0 possible triangles. Like this one didn't even work out at all, and the one before it, we knew could only have one possible triangle because that angle they gave us was obtuse. So those weren't the best examples, but now we have an ambiguous case, and there could be a second possible triangle. So here's how and why we check for a possible second triangle. It comes down to this step right here. We took the inverse sine or the arc sine of some value. And remember that on the unit circle, the arc sine range is only in the first and the fourth quadrants there. So when you type that into your calculator, it's only ever going to give you one answer. So it told us that there's some angle that has this positive sine value. And so it's somewhere up here, right? Because we got 10.2 degrees, somewhere in the first quadrant. But we know that outside of the first quadrant, there's this other angle over here that has the same sine value, right? Because the sine is like the y value. So they have the same sine value. It's just our calculator is never going to give us this second angle because that's not in the arcsine range. So think of it this way. Our calculator gave us this angle A, but there's like a second possibility. I like to call this A prime, or just label it with like this prime notation just to mark them as different. If you want to call it A2 or whatever, just make sure that you can tell the difference between them. So this is like our second possible angle A. So in order to get that, we're looking for this angle here. I'm just going to take this size angle, so the 10.2 that the calculator gave us, and subtract it from 180. So 180 minus the calculator's answer, and that would give us 169.8 degrees. And I'm still at the point where I'm checking for the second triangle. I don't know if it exists yet. If it does exist, that means that I would have this angle A prime in this triangle, and I would also have the angle B that they gave us in the beginning. So if we just bring that down here, I now have these two angles, and then the third angle in the triangle, I'm going to call that C prime, since we're kind of working in this like prime triangle. I still call this regular B though, just because that's the same angle B that they gave us. But if I'm looking for C prime, all three of these angles have to add up to 180. So I could say 180 minus the 15.5 from the beginning, and then also minus the 169.8 that we just got. But if you do that, you get negative 5.3 degrees. So obviously this is not possible. But the only way to know is to just check. So we don't have to worry about any of this stuff. We don't have to worry about that second triangle, but we haven't finished solving our first triangle. We have angle B, angle A. We need our third angle. That'll be really easy to find. We can just subtract the two we know from 180. So we get 154.3 degrees. And then we just need our last side. So we have side A, side B. We need side C. So I'll put side C on top of the fraction, sine of angle C on bottom. So sine of 154.3 degrees equals, and then pick a pair of information that they gave you in the beginning, so angle B and side B. And to solve this for C, you just have to take this sine of 154.3 and multiply it over to the right side. And typing that in your calculator should get you 11.0. And I'm writing 11.0 because there were more numbers after that, and I want to do this to show that I'm rounding this to the 10th place. So that just means that whatever numbers came after this were like less than 5, so it would round this back down to the 0. So there's our one possible triangle. Our last example is going to have two solutions, as you might imagine, so I'm just giving myself a little bit more space here. And we're going to follow the same procedure we just followed, where we have to check for that second triangle. So let's get started. We have angle A and side A. That's the pair that I'll put together. I have side B, so let's look for sine of angle B first. Sine of angle B over side B, which is 5, equals, and then sine of angle A, so 58 degrees, over side A. Let's multiply this 5 out of the denominator, and then take the inverse sine of both sides. So we get 70.4 degrees. Now there's our first angle B, but remember there's a second possible triangle, so I like to check for that right away. So I'm going to call this B prime. And remember that there was that second spot on the unit circle, like our first angle was 70 degrees, but there's another spot on the unit circle that has the same sine value. So we'll take 180 degrees minus the answer that we just got, 70.4, and that gets us 109.6. So it's almost like we have these like two alternate realities going on, these two possible triangles happening at the same time. Let's just go back to the first one. We have angle A, we have angle B. Let's figure out angle C right away. So C would be 180 degrees minus the angle A that we already know, so 58 degrees, and then also minus the 70.4 that we found out. Doing that should get you 51.6 degrees. The last thing we need for this first triangle is side C, because I already know side A and B up here. So to figure that out, we'll do side C over sine of that angle we just found, so 51.6, equals, and then let's take a pair of information we already know from the beginning, so 4.5 over sine of 58. So then you just want to multiply the sine of 51.6 over to the right side. Type that in your calculator and you should get 4.2. So that finishes out our first triangle. Now jumping back to the second triangle, we already have angle B prime, and we already have the angle A from the beginning of the problem. Remember they told us that was the 58 degrees. So we have two of the angles in this triangle. Let's figure out the third one, which I'm going to call C prime. So all three angles have to add up to 180. So I'm just going to subtract out the 58 and subtract the 109.6. And that should get you 12.4 degrees. And make sure you're using the degree sign on these angles because it's kind of hard to tell the difference between a capital and lowercase c. The next thing we actually have to find is side C. So lowercase c, make sure you put the prime though. And then over sine of 12.4. That's the angle we just found. Again, use a pair of information you know now, so we'll say 4.5 over sine of 58 degrees. Just multiply the sine of 12.4 over to the right. And when you type that into your calculator, you should get 1.1. And that finishes out our second triangle. All right, hopefully this will help get you started solving triangles using law of sines.